Hello, this is Jake Abbott. In this video, we're going to be talking about discrete systems. We've been, at this point in the sequence, we've learned about state space equations, which are sets of linear time varying or linear time invariant first-order differential equations. We've also talked about, very briefly, about the transfer function, which is a way you can think about input-output mappings of these linear systems using Laplace transforms. In this class, unlike other classes that you might take, like a classical control class, rather than doing everything in time domain and then sort of at the very end thinking about how to describe things in discrete time, using things like a Z-transform, which you may have seen. In this class, we're going to handle discrete systems right along with the continuous time systems. They end up being mathematics in the state space controls formulation ends up being very similar between the two, so we can just handle discrete systems as we go along. So when I say discrete system, what I'm really talking about now is something that looks like this. It's a very similar form. We have an x vector, but instead of an x dot vector, we're going to be analyzing our state vector x at some sample at k plus 1, basically meaning the next sample. And that's going to equal some matrix A times our state vector at sample k. And I'll talk in a minute about what this sampling means. Plus b times our input vector at sample k. And typically use square brackets here instead of sort of parentheses. It's just a convention. And then we'll have our output vector, y at sample k is equal to c, x at k, plus d, u at k. So in a lot of ways, this looks very similar to the time-varying case that we saw earlier. Again, I've made my A, B, C, and D matrices be constants, which means this is really an LTI system. I'm looking at a linear time-varying system. But we could consider linear time-varying systems in which A, B, C, and D would also be changing as a function of the sample k. So I say the sample k here, and what does this mean? In discrete systems, unlike continuous time systems, we don't think about our signal, our x's and our u's and our y's, evolving over time in a way that you could get a continuous time-varying plot like this, where you have time and you have some signal that's sort of smoothly evolving over time. Instead, you think of things being updated in very discrete units. You can still think of them as instants of time, but now instead of varying continuously, maybe k represents a year. Maybe this is a financial model, and you have an interest that's updated once per year. So it basically says, what will the money in my account be next year at sort of sample k plus 1? And you say, it's whatever I have in my account right now times 1.02. That would be a 2% interest. Maybe k represents a quarter, though, and you have the same exact formula. You say my money in my account next quarter will be whatever's in my account now times 1.02, so I'm earning 2% quarterly. So I'm updating in samples. This also lends itself to think directly about computer code, because the computer doesn't really, as it's running through lines of code, it doesn't really think about time so much. It just says, when I want to calculate a given line of code, I just take the numbers that I have stored in my memory, and I do my operation on them, and I store that new value in memory. And so discrete systems sort of lend themselves well to thinking about computer code. So in some regards, these k's are now instances, and they're usually still instances of time, but we very much disconnect ourselves from time. We can think about it without knowing how much time has passed from k to k plus 1. Maybe it's been a year, maybe it's been a second. It's sort of, it doesn't matter. We can analyze our system also without knowing that. But the big difference here, of course, is that these are no longer differential equations. This is not an equation for x dot. It's an equation for x at k plus 1. But if you think about what the state space equation is really saying, which is, how do my states evolve? That's what x dot told us. It says, how's x changing? That's what the dot is, its derivative. How is it changing? And it's changing as a function of the current state values and the current input values. But we're still doing that here. We're still saying, how are our states changing? So we're saying, what will our states be next time? Well, that's a function of what they are right now and what the inputs are. So the state equations are very much still descriptions on how our states are evolving in time as a function of state and input. So in that regard, it's very similar. So these are the kind of systems we're going to be looking at in discrete time. And like I said, we'll just be analyzing these in parallel for continuous time systems. So I think it would be interesting to sort of think about how one might formulate state space formulation of a problem. So let's make up a toy problem. I'm a principal of a high school, and I want to keep track and try and model and predict what my enrollment in my high school is going to be. Okay, so I'm making up a problem here, and I really have 3 grades. Okay, so let's call state 1 the number of sophomores. Let's say I'm in high school, that's 3 grades: sophomores, juniors, and seniors. So x2 is going to equal the number of juniors. Apparently I'm in England or something, so I write juniors with a U. And then x3 is going to equal the number of seniors. And as the principal, let's say I'm really interested in the total population of my school at any point in time. So the output I'm going to be interested in is x1 plus x2 plus x3. So that's just the total population of my school at any given year. And then we have to think about what our inputs to the system are. Well, let's say we have U1 is equal to the number of junior high graduates. Junior high graduates. So there's going to be a bunch of kids in a given year coming out of junior high, and those kids that are coming out of junior high are going to become sophomores of my school. But they're not all going to come. There's going to be some percentage that leave, and so let's try to account for that. And let's say U2 is equal to the number of families with high school aged kids moving to the district. So there's sort of 2 ways that you can add as suits to your school. You can have them coming up from the junior high, or you can have families move into your district, and U2 being negative would be families moving out of your district. And we'll just make the assumption, we'll just do a rough assumption that of all the families coming into your district, or moving into your district, or leaving your district, there's sort of an equal probability that if they have high school age kids, equal probability that the sophomore or junior or senior year. So okay, I think we've got enough structure here to think about this. So let's clean this slide. So let's think of what the equation for our sophomores. So sophomores were our state x1. And let's think about x1 at k plus 1. So how many sophomores will there be next year? Well, it's basically U1 at k. So that's how many students are graduating from junior high this year will become sophomores next year. But they're not all going to come in, so we're going to have to put some percentage of how many kids from the junior high actually come to high school. Some are going to move away. We'll account for moving away in the other number. So let's just think of sort of the dropout rate here. But I think not very many kids drop out at this age. So let's say this is like 0.99. So almost all of the kids who are graduating from junior high this year will become sophomores next year. And then we do have this influx of families moving in or leaving the area, and we call that U2 this year. So how many people are moving in this year? And let's just say a third of those families, sort of equal probability, that have high school age kids, a third of them will be sophomores. So now we have an equation for how many sophomores there will be next year. So what about juniors? So juniors next year is going to equal some percentage of the sophomores this year. So here are sophomores this year. And what percent of sophomores do you think drop out and don't go on to juniors? Let's say 95% go on to becoming juniors. And then we also are going to have a third of the students who are moving in. So U2 represents the number of families with high school age kids that are moving in, and approximately a third of them, the high school age kids, approximately a third of them will be juniors. And so now we have for 95% of sophomores are going to move on to being juniors, and 5% will drop out, let's say. And I think this is good. And then let's write our equation for seniors, and that's how many seniors will there be next year. And I think we probably make some sort of similar number, let's say. So 95% of this year's juniors will move on to being seniors, and then another third of our families moving into the district with high school age kids, a third of them will be senior age kids. And then we said we wanted our output to be the total population of the school. So in any given year, our output at year K is going to equal the number of sophomores that year, plus the number of juniors that year, plus the number of seniors that year. And so now we can start packing this into our state space formulation for discrete systems. So sophomores, juniors, and seniors, and I'll just write this whole thing at sample K equals 1 is going to equal some big A matrix. And just like before, this is going to be a square matrix. In this case, it's going to be a 3x3 square matrix. And then I have my sophomores, juniors, and seniors, and this whole vector is at some K. And I'm going to have 3 states and 2 inputs, so I'm going to have a big 3 by 2 matrix here times my 2 inputs, U1 and U2 at sample K. And then let's figure out our governing equations. So x1 at K plus 1 is 0.99 times U1, 0.99, and it's 0.33 times U2, and it's not a function at all of the states. So 0, 0, 0. My equation for x2 next year is 0.95 of x1 and 0.33 of U2. It's not dependent at all on x2 or x3. And then x3 is 0.95 of x2, and then 0.33 times U2. So we've packed our A and B matrix now, and then our output, which is simply the sum of the 3 states, is going to be 1 by 3 vector, x1, x2, x3, and it's just going to be 1, 1, 1, the sum of the 3 states. I'm not even going to bother packing on a D matrix, because in this problem, like in so many problems, it's just 0. We're not going to be really concerned about looking at our inputs coming out in our outputs. And then you can kind of sort of imagine what would have happened if we would have said, in our senior year, not only do we have 95% of our juniors coming forward, but what if we would have said that in any given year, 5% of our sophomores skip a grade? So our sophomores are x1. So we could have made our equation more complicated and said 5% of our sophomores just become seniors directly. And so we could have come in here now, and the 0 here would become 0.05. So you can see how making sort of changes to your equation change this A matrix, and ultimately it's going to be these A's and B matrices that this power system is going to evolve in time. So this is how you formulate discrete problems, and the cool thing about this, when you start thinking about these problems that at first don't seem like engineering problems, you can sort of start thinking about doing social engineering and financial engineering. I mean, if you're the principal of the school, think what this means. I mean, what would we talked about the 0 state response and the 0 input response. So what would the 0 state response correspond to here? That would be a system in which, at the beginning, all of my states are 0. So that would be like I'm opening a new school. Like I've gone out to some development, I built a new development where people are going to move to, and I build a big school, and my school is going to be populated by people moving into the area. So I'll have this input U2, and there may be some junior high that feeds, I'm not sure about that, but basically I have this input U2, my state is 0, and I could watch how my population of my school evolves over the first few years as I have people start moving into this area. What would the 0 input response mean? So I basically start with some initial condition, I have a school population that's well established, and I start making my inputs 0. Well, I mean, U1 equals 0 means you're not taking any more students from a junior high. It's almost like you're saying you've decommissioned your high school or something. And what would U2 being 0 mean? It means you got a bad economy and no one's moving to this neighborhood anymore. There's no net influx. There's no more growth. So that would be the 0 input response. And you could say, if no one ever moves into this neighborhood again, and I start with some population, how will the population of the school evolve over time? So I'm hoping you're starting to see how these tools that we learned in this class, you can think about more broadly than just mass spring damper systems and sort of mechanical systems that we might cover in sort of kind of simple engineering examples.